When we listen to the universe, we do not hear words or music. We hear patterns. We hear numbers. We hear signals that at first often sound wrong. Today I want to tell you about a signal that cosmology almost ignored because it did not fit what we expected. A signal that said the universe is not just expanding, but accelerating. A signal that forced us to accept something we now call dark energy. And along the way, I want to show how this connects to dark matter, gravity, space-time, and the possible fate of the universe. Let me start with what we thought the universe was doing before this signal arrived. For most of the 20th century, the basic picture was simple. The universe is expanding. Galaxies are moving away from each other. This was discovered in the 1920s by Edwin Hubble and others, who measured that the farther a galaxy is, the faster it appears to recede from us. The light from these galaxies is redshifted. Its wavelength is stretched by the expansion of space-time. That pattern is called Hubble's law. If the universe is expanding and if gravity is always attractive, then there is a natural expectation. Over time, the expansion should slow down. The matter in the universe pulls on itself. That pull fights against expansion. So for decades, the main question was not, is the universe slowing down, but how fast is it slowing down? Would gravity eventually stop the expansion and cause a recollapse? A big crunch? Or would the expansion go on forever, but at a decreasing rate, approaching a kind of coasting state? To answer that, cosmologists needed two key numbers. One was the Hubble constant, which tells us the current rate of expansion. The other was the average density of matter and energy in the universe, which tells us how strong the overall gravitational pull is. If the density is high enough, gravity wins and the universe eventually recollapses. If it is low, the universe expands forever. That was the framework. No one seriously thought the expansion might be speeding up. Now, how do we measure the expansion history of the universe, not just its current rate? We need standard candles. Objects whose true brightness we know, so that by measuring how bright they appear, we can infer their distance. Then we compare that distance to their redshift, which tells us how much the universe has stretched since their light was emitted. If we can do this for very distant objects, we can reconstruct how the expansion has changed over billions of years. In the 1990s, two major teams set out to do exactly this using a special kind of exploding star, Type 1a supernovae. These supernovae occur when a white dwarf star in a binary system accumulates matter from its companion until it reaches a critical mass and undergoes a thermonuclear explosion. The physics of that process tends to produce a similar peak brightness each time. After some careful calibration, Type 1s supernovae can be used as standard candles, or at least standardizable candles. If we know how bright they should be, and we measure how bright they look, we can estimate their distances across billions of light years. The plan was straightforward. Measure distant Type 1a supernovae, plot their distance against their redshift, see how much the expansion has slowed. Use that to determine the matter density of the universe and its fate. The expectation was that distant supernovae, whose light left them when the universe was younger, would show that in the past the expansion was faster and has been decelerating over time. When the first data came in, the signal looked wrong. The distant supernovae were too faint, not just a little, systematically. For a given redshift, they appeared farther away than expected in a decelerating universe. The simplest interpretation was that the universe had expanded more than our models predicted. That means the expansion had not been slowing down as much as we thought. In fact, the data were best explained if the expansion had started to speed up in the last few billion years. This was the signal we almost ignored. Not because people literally threw away the data, but because the first reaction was, what systematic error did we miss? Maybe the distant supernovae were different from nearby ones. Maybe dust between us and them dimmed their light in a tricky way. Maybe selection effects biased the sample. Maybe the calibration was off. Every experimentalist and theorist knows that when a result contradicts decades of expectations, the first suspect is the measurement, not the universe. The team spent years trying to break their own result. They checked for dust with unusual properties. They looked at supernovae in different types of host galaxies. They used different analysis methods. Independent groups repeated the observations. Other telescopes confirmed the pattern. The signal refused to go away. The distant supernovae really were too faint. The universe really looked like it had expanded more than a decelerating model allowed. At this point, the community had a choice. Either there was some unknown, very specific systematic effect in multiple independent data sets, or the basic assumption that gravity always slows expansion was incomplete. The second option led to a remarkable idea. What if there is a component of the universe that does not clump like matter, that does not dilute in the same way as space expands, and that exerts a kind of negative pressure? In general relativity, pressure gravitates. Positive pressure adds to the attractive effect of gravity. But negative pressure can act effectively as a repulsive component on cosmological scales. If such a component dominated the energy budget of the universe at late times, it could cause the expansion to accelerate. We call this component dark energy. The simplest model of dark energy is a cosmological constant. This is a constant energy density of empty space itself. It was actually introduced by Einstein in 1917 as a mathematical term in his equations of general relativity to allow for a static universe. When Hubble discovered expansion, Einstein reportedly called it his biggest blunder, and many people dropped the cosmological constant from their thinking. But mathematically, it never went away. The equations of general relativity allow a constant term that acts like a uniform energy density with negative pressure. When the supernova data suggested acceleration, the cosmological constant suddenly became relevant again. If dark energy is a cosmological constant, its energy density stays the same as the universe expands. Meanwhile, the density of matter, both normal and dark, decreases as the universe grows because matter is spread over a larger volume. That means that in the early universe, matter dominated and gravity slowed the expansion. But as the universe expanded and matter diluted, the constant dark energy density eventually overtook matter and began to dominate the dynamics. At that point, the expansion started to accelerate. The supernova signal, which at first sounded wrong, fit this picture beautifully. But science does not rest on one type of observation, so cosmologists looked for independent evidence. One powerful test comes from the cosmic microwave background, the afterglow of the Big Bang. This is radiation released when the universe was about 380,000 years old, when electrons and protons combined to form neutral atoms and the universe became transparent to light. The tiny fluctuations in the temperature of this radiation across the sky encode information about the geometry and contents of the universe. If the universe is spatially flat on large scales, as predicted by many inflationary models, then the pattern of these fluctuations has a characteristic angular scale. Observations from satellites like COBE, DOMAP, and Planck measured this pattern with high precision. The data show that the universe is indeed very close to flat. In general relativity, flatness implies that the total energy density of the universe equals a specific critical value. But when we add up the density of normal matter and dark matter from galaxy rotation curves, galaxy clusters, and large-scale structure, we only get about 30% of that critical density. Something else must provide the remaining 70%. The simplest fit is a cosmological constant, or dark energy, making up about 70% of the total. Another, very different line of evidence comes from baryon acoustic oscillations. In the early universe, before recombination, normal matter and radiation were tightly coupled, forming a hot plasma. Sound waves traveled through this plasma, driven by the competition between gravity pulling matter together and radiation pressure pushing it apart. When the universe cooled enough for atoms to form, these sound waves froze in, leaving a preferred scale in the distribution of matter. Billions of years later, we can see this as a slight excess probability of finding galaxies separated by about 150 megaparsecs. This acts as a standard ruler. By measuring how this scale appears at different redshifts, we can trace the expansion history. Those measurements also support an accelerating universe dominated by dark energy. So we now have a coherent picture. The universe is about 13.8 billion years old. It is expanding. The expansion is accelerating. About 5% of the energy content is normal matter. About 25% is dark matter, which interacts gravitationally, but not, as far as we know, electromagnetically. About 70% is dark energy, which drives cosmic acceleration. The geometry is close to flat. This model is called lambda CDM, where lambda stands for the cosmological constant and CDM for cold dark matter. But calling it a model does not mean we truly understand what dark energy is. We know its effects on the large-scale dynamics of spacetime. We can measure its density parameter. We can infer that its equation of state, the ratio of pressure to energy density, is close to -1, as expected for a cosmological constant. But we do not have a direct detection in the lab. We do not have a fundamental theory that explains its tiny but non-zero value. Here is one of the biggest puzzles. In quantum field theory, empty space is not truly empty. Quantum fields have zero-point energies. If we naively add up these contributions, we get a vacuum energy density that is enormous, many orders of magnitude larger than the observed dark energy density. Depending on the cutoff scale you choose, the mismatch can be 60 to 120 orders of magnitude. This is sometimes called the worst theoretical prediction in physics. Something in our understanding of quantum fields, gravity, or both is incomplete. The cosmological constant problem is not just why is dark energy there, but why is it so small and yet not exactly zero? Before I go deeper into that, I want to connect dark energy to dark matter and gravity. Because they form a single story about how we infer invisible components from their gravitational effects. Dark matter was proposed earlier in the 1930s and 1970s to explain why galaxies and clusters behave as if they contain more mass than we can see in stars and gas. Galaxy rotation curves stay flat at large radii instead of dropping, as they would if only visible matter were present. Gravitational lensing, where massive objects bend the path of light, reveals more mass than luminous matter accounts for. The large-scale structure of the universe, the cosmic web of galaxies and filaments, also points to a dominant dark matter component that seeded structure formation. Dark matter clumps under gravity. It forms halos around galaxies. It enhances the gravitational pull that shapes the motions of stars and gas. Dark energy, in contrast, does not clump on small scales, as far as we can tell. It is smooth and uniform. On the scale of galaxies, its effect is negligible compared to gravity from matter. On the scale of the observable universe, it dominates the dynamics. So, when we talk about the fate of the universe, we are really talking about a competition between the gravitational attraction of matter, including dark matter, and the repulsive effect of dark energy on cosmic scales. In general relativity, gravity is not a force in the Newtonian sense. It is the curvature of spacetime caused by energy and momentum. Matter tells spacetime how to curve. Spacetime tells matter how to move. When we say the universe is expanding, we mean that the metric that defines distances between moving points is changing with time. Galaxies are not flying through space away from each other like shrapnel. Instead, the space between them is stretching. In that framework, dark energy acts as a property of spacetime itself. It changes how the metric evolves. If dark energy is exactly a cosmological constant, the future is relatively simple to describe. The expansion will continue to accelerate. Distant galaxies will recede faster and faster. There is no contradiction in saying that distant galaxies can recede from us faster than the speed of light, because this is not motion through space. It is the expansion of space itself. There is a cosmic horizon, a distance beyond which light emitted now will never reach us in the future, because the space in between expands too quickly. Over time, more and more galaxies will cross that horizon. They will fade from view, not because their light stops, but because their light can no longer overcome the expanding space. In the far future, observers in a galaxy like ours would see only their local group, which by then will have merged into a single massive galaxy. The cosmic microwave background will be redshifted to wavelengths so long that it will be essentially undetectable. The universe will look empty and static on observable scales, even though the global extinction scenario is sometimes called the Big Freeze or heat death. As stars burn out, as matter is slowly consumed or decays, the universe approaches a state of maximum entropy. Energy is still conserved, but it is spread out so uniformly that no large-scale structures or processes can extract useful work from it. On very long timescales, black holes evaporate through Hawking radiation. Eventually, only a thin bath of low-energy photons and other light particles remains. That is one possible fate, and in the lambda CDM model, it is the default. But this fate depends on the nature of dark energy. We do not know for sure that dark energy is a pure cosmological constant. Observations measure its equation of state parameter, usually denoted W, which is the ratio of pressure to energy density. For a cosmological constant, W equals 1 exactly. Current data are consistent with W minus 1 within a few percent, but there is room for small deviations. If W is slightly greater than -1, dark energy might slowly dilute or change over time. If W is less than -1, that is a more exotic case often called phantom energy, which could lead to a future big rip, where the expansion accelerates so violently that eventually even bound structures like galaxies, solar systems, and atoms are torn apart. Right now, the data do not demand such extreme scenarios, but they cannot fully rule them out either. So we face a series of layered unknowns. What is dark matter? We have strong evidence that it exists and that it is not made of normal baryonic matter like protons and neutrons, but we have not yet detected a dark matter particle in the lab. Many candidates exist, from weakly interacting massive particles to axions to more exotic possibilities. What is dark energy? Is it a cosmological constant, a quantum vacuum energy, a dynamic field, or a sign that general relativity needs modification on large scales? Why is its energy density so small? Why did it start to dominate only relatively recently in cosmic history, long after the formation of galaxies and stars? That last point is sometimes called the coincidence problem. If dark energy is constant in time, while matter density decreases as the universe expands, there is only a relatively narrow window in cosmic history when the two are of the same order of magnitude. We happen to live in that window. Billions of years earlier, matter dominated. Billions of years later, dark energy will dominate even more strongly. Is this just a coincidence, or does it hint at some deeper connection? We do not know. Some theories try to link dark energy to the formation of structure or to anthropic arguments, but none are universally accepted. Let me step back and connect this to the idea of a signal we ignored because it sounded wrong. In science, we build models based on existing data and theory. Those models shape what we expect new measurements to look like. When a new signal arrives that does not fit, we have to be careful. The first duty is to the data quality. Are we sure the measurement is reliable? Are there hidden biases? Are we interpreting the signal correctly? Only after we have tested and retested the data do we consider modifying the underlying theory. In the case of cosmic acceleration, the supernova signal was surprising, but it did not stand alone for long. It was joined by independent evidence from the cosmic microwave background, from galaxy clustering, from gravitational lensing, and from other probes. Together, these signals formed a coherent picture that demanded dark energy or something very similar. The reason this is important is that it shows how cosmology is not just storytelling. It is a quantitative science grounded in multiple, cross-checked observations. We can ask a similar question about dark matter. When galaxy rotation curves looked wrong, when clusters of galaxies seemed to have missing mass, some people proposed modifying gravity instead of adding unseen matter. Modified gravity theories, such as MOND and its relativistic extensions, try to explain these phenomena without dark matter. They can fit some galactic scale data, but they struggle to explain all observations simultaneously, especially the cosmic microwave background and large-scale structure. The current consensus is that dark matter is real, although the door is not fully closed on modified gravity ideas. In both cases, dark matter and dark energy, the signals forced us to consider components of the universe that we do not directly see, but that reveal themselves through gravity. Gravity itself, as described by general relativity, has passed every local test we have thrown at it. From the precession of Mercury's orbit to the bending of light by the sun, from the time dilation measured by GPS satellites to gravitational waves detected by LIGO and Virgo, the theory works extremely well. But we have not yet tested gravity directly on the largest cosmological scales with the same precision. It is possible, though not yet necessary from the data, that general relativity needs modification in that regime. Some alternative theories of gravity can mimic dark energy without introducing a separate fluid. They change the way spacetime responds to matter and energy on large scales. Observations of the growth of cosmic structure over time and of how matter clusters under gravity are being used to test these ideas. This is why current and upcoming surveys are so important. Projects like the Dark Energy Survey, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, the Euclid mission, and the Nancy Grace Roman Space Telescope are mapping billions of galaxies, measuring weak gravitational lensing, tracking baryon acoustic oscillations, and monitoring supernova. They aim to pin down the properties of dark energy and test general relativity on cosmic scales. We are listening more carefully to the universe's signals with better instruments and better analysis. There is another subtle signal that has emerged in recent years, related to the Hubble constant. Different methods of measuring the current expansion rate of the universe give slightly different answers. When we infer the Hubble constant from the cosmic microwave background, assuming the standard lambda CDM model, we get one value. When we measure it directly using nearby supernovae and other distance ladders, we get a higher value. The difference is not huge, but it is statistically significant. This is known as the Hubble tension. This tension might be a sign of unknown systematics in one or both methods. Or it might be a hint that the standard model of cosmology is incomplete. Perhaps something about the early universe, or the behavior of dark energy, or the properties of dark matter is different from what we assume. Right now, the community is in the middle of this puzzle. We are cautious. We do not want to declare a revolution prematurely. But we also cannot ignore a persistent, well-checked discrepancy. It might be another signal that sounds wrong at first, but points to new physics. Throughout all of this, the key idea is that space-time is dynamic. It evolves. The universe is not a static stage on which matter moves. It is an active participant. The distribution of matter and energy, including dark matter and dark energy, determines how space-time curves and stretches. That curvature and stretching, in turn, guides the formation of galaxies, the motion of clusters, the propagation of light, and the very concept of distance and time on cosmic scales. When we talk about the fate of the universe, we are really asking how this dynamic spacetime will behave in the far future. Will the acceleration continue forever, leading to a cold, dilute universe where structures are isolated and eventually fade? Will dark energy change sign or weaken, allowing gravity to slow or reverse the expansion? Will new physics emerge at very low densities or very large scales that we cannot yet see? Our current best model points toward eternal acceleration and a big freeze. But that answer rests on the assumption that dark energy is a constant and that general relativity holds unmodified on all scales. We know from the history of physics that theories can be incredibly successful within a domain and still be incomplete. Newtonian gravity works very well for most everyday and solar system phenomena, yet it fails when we approach the speed of light or very strong gravitational fields. General relativity extends and replaces it, but we also know that general relativity is not yet unified with quantum mechanics. At very high energies, very small scales, or perhaps very large cosmological scales, something new must happen. Dark energy might be one of the clues pointing toward that deeper theory. So we are left with a universe where most of the energy content is in forms we do not fully understand. Dark matter, which shapes structure. Dark energy, which shapes expansion. Gravity, which we describe geometrically but have not yet quantized.